So today we learned about a kind of a mathematical proof, or a way to prove things in math. And it's something that we don't do much anymore. It used to be, like when I was a kid, that geometry was almost exclusively about proving theorems to be true, right? And that is such a different way of doing things than algebra that it really kind of takes a different kind of thinking for that. And I remember when I was at Kansas State University, and at the time I was majoring in math education, I think, and they were making me take a class in the history of math. And it was a small class, and the professor was digressing. We were just chatting about stuff. And we were chatting about students that went from being undergraduates in math to getting masters and PhDs. And he said that in order to find who had the right aptitude for doing that kind of thing, they would have to go back to like a high school geometry class, because most everything else that you do in math is really more of that algebra to calculus kind of thing, which is not the same kind of thing at all. And this is one way to prove things. It's not like anything we did in geometry or anything like that, but real mathematicians are much more interested in like how do you take things you know to be true and construct other things you know to be true, not just taking formulas and doing number crunching and things like that. That's an accountant or something like that. It's not interesting. It's just, it is what it is. But so this will be much different than that. I would say that sometimes when I go into this lesson, I think that you're not going to like it, and then usually I find that you do. That most say, oh, this is not bad, And we use it a little bit. I'll show you when we end up using this later on. The fact that we have proved some things to be true, then we do that. So let's see. If you look at this pattern, right, of a sequence of numbers which is being added up, right? Here's the sum of one term in this sequence. 1. Okay. S2 is 1 plus 3, right? S3 is 1 plus 3 plus 5. Right? You can notice the pattern: 1 plus 3 plus 5 plus 7. You see the pattern of the terms here? It looks like we're adding up the first so many odd numbers. Okay? And notice that when you do that, like you get 1 is 1 squared. 1 plus 3 is 4, but that's 2 squared. 1 plus 3 plus 5 is 9. That's 3 squared. And you could just, and so on, right? Even all the way down to here. If you add up these numbers, you get 36, and that just happens to be 36 squared. So the general pattern here is that if you add up the first n terms, right, the nth term would be represented by this formula. This is the a sub n. This is the formula that would generate the last term. And if you're not sure, you could try it. Like for S6, that ought to be generating 11 to be the sixth term. Okay, 2 times 6 minus 1 is 11. So it seems like it's generating the right numbers there. And then the formula for the right-hand side is n squared. When we plugged in 1, it was 1 squared. 2, 2 squared. In every case, it looks like you don't actually have to go through this whole mess to add them up. What kind of a sequence is that we already studied? It's arithmetic. We keep adding 2 to get the next term. So, in the end, we have a formula for that. And you could definitely use the formula. But actually, this one in particular, there's a much easier way to do it. Just square it. What if you want to do S20? 20 squared, 400. Done. You don't actually have to use that formula or add them up. So this formula over here, this n squared, that is a formula for the sum of the first n terms. Now, the fact that you could do that for n equals 1 to n equals 6, does that prove that it's true for all values of n? No, it doesn't. It's nice, but how many do we need to not be true to disprove this whole thing? 1, right? So in the end, you could keep checking to see if you could find one where it doesn't work, or you could come up with a way where you can prove that actually this one will work for all values of n. An example of one that didn't work, that they thought worked, this is taken from your textbook if you wanted to see more of the details, because I didn't reread it right now. But this was supposed to be a formula to generate prime numbers. And it was made by a guy named Fermat. It was around in, I think, the 1600s or something like that. And it's like, if you use this formula, 2 to the 2n plus 1, his theorem was this would always generate a prime number. Okay. Now, the problem with this is these numbers get really big, really fast. And now they could show that it worked for 0. I mean, 2 to the 0 is 1. 2 to the first is 2. 2 plus 1 is 3, right? And that's prime. And you can show that it works for 1, and you can show it works for 2. I mean, those are all numbers we know are prime. When the numbers start getting big like that, we're not that familiar with them, but it wouldn't take too long to show that 257 is a prime number. 65,537, that's a little bit harder to tell. But even in those days, they were able to show that that was a prime number, okay? But they couldn't get at that number. I mean, they could make the number. They could plug in 5 and generate that number, but they couldn't tell if it was prime. Because how are you going to tell if it's prime? Test every number less than it to see whether it's a factor? It took them about 100 years before somebody was able to actually find the factors of that. It was not prime. So just because they could use this formula from n equals 0 to 4 did not mean it was going to be true for all n. That's why you're going to use a formula for something. You got to know that it's true all the time, not just all the times that you checked. That doesn't prove anything, right? So that's why we come up with this thing called math induction as a means of showing when you're doing using formulas for a sequence to generate a sequence of numbers that this works. That's kind of why this fits into the chapter on sequence and series. So math induction, the way we're going to do this is there's 2 steps, basically. The first step is we're going to show that the formula that we're trying to prove is true works. And generally they say for n equals 1. That's what this is saying right here. You show that it works for the first value, for the first term. And then show that if you assume it works for the nth term, that it must work for the n plus 1 term. Right? If you assume it's true for one term, then it must be true for the next term. Because if you can do that, if you can show that there's a link between any 2 of these terms in the sequence, the fact that you already showed that it works for 1 means it must be true for 2. And because it works for 2, it must be true for 3. And because it works for 3, it must be true for 4. It's kind of like dominoes, right? Once you get that first one fallen, they're all going to fall. As long as you can show that there's this link in between any 2 of them, it'll work. So again, first you try to make, make sure it works for the first number. And then show that if it works for any particular number, it must work for the next number. If you can show that, then you've shown it works for all values. And don't be confused too much about the k. We're using k this time, k plus 1 for the next term. It could be n plus 1. I tend to always use n, but sometimes in the book examples, they're using k. It doesn't make too much difference. But I mean, this is kind of where this whole thing about recursive formulas, which confuse us a lot. I think it tend to confuse us in this too, because you do end up having to do things like in that sense of, just understanding how you go in a general sense from one term to the next, n to n plus 1, k to k plus 1, things like that. So this will, as we do a few of them, this will become more clear, and I think you'll probably think it's not that hard. I hope. So now this first example, which is just a matter of showing if you're saying we have a statement which is true for k. If you just want to say what would the k plus 1 representation of that look like, then that just means you need to substitute k plus 1 for k. Right? If this is what it looks like for k, what would it look like for k plus 1? sk plus 1 would be, in place of the k, put a k plus 1. Right? Over here where it says k plus 1, put k plus 1, but then that will be k plus 2, because a k plus 1 will be k plus 2. And that was squared. And the 4 stays the same. Right, so this is what it looks like for k. This is what it looks like for k plus 1. You just put k plus 1 in place of the k. Right. Here's the statement for sk. Right. Just really, it's the sum of all these things right here. If I was going to do sk plus 1, that means it would have one more term on the end. I mean, this must be right here. This must be the ak term. Right? If I want it to be the sum of the first k plus 1, then what am I going to add to that? I'm going to add one more term, and that's going to be 4 times k plus 1 minus 3. Okay. Now that's the sum of the first k plus 1 terms. Right? By adding the one more term, the a k plus 1 term, now I've got the sum of the first k plus 1 terms. Okay. Here's some inequalities, which we're not going to do anything with the inequalities in the proofs, but still, principle's still the same, right? If this is the statement for k, what would the same statement look for k plus 1? In the place of k, put a k plus 1, so the left becomes k plus 4, right? K plus 4 is less than 5 k plus 1 squared. And this one, 3 to the k plus 1 is greater than or equal to 2k plus 1, k plus 1, plus 1. So just a little practice at going from kth term to the k plus 1 would be the same thing if I was saying n and n plus 1. Same deal. Okay. Where? Here? Well, I would have to say 2k plus 2, which would be 2k plus 3. You could simplify it. Okay. So here's where we're going to actually use this math induction. Okay. So the first step, again, the first step is show that this formula, okay, so S sub n is the sum of, and this is actually the one that we had in the example at the beginning, right? The sum of the first n terms can be calculated using this formula, n squared, right? So this is my an. This is the Sn. Okay, so the first step in math induction would be show that this formula works for n equals 1. Okay, so for n equals 1, which we've already seen this, you could just look, the sum of the first term, just looking at it, is going to be 1. The first term is 1. The sum of it is 1, right? Okay, well, plug in n equals 1 to the formula. 1 squared, which is 1. So for n equals 1, we're going to say 1 equals 1 squared, check. Okay, that's all you end up ever doing. Most of the time, we forget to do that step, you know, because it always works anyways. But that's what they mean by that first step. Show that it works for n equals 1. That's the first domino, right? Okay, now we have to assume that it's going to work for n, and then show that it'll work for n plus, that means it must work for n plus 1. And this is what that looks like. Kind of don't like the way this was written there, but let me do this. I'm going to write this over here. Equals n squared see if I can do this. I don't know if I could do this. I've been playing around with this. let's see. Okay, so if we write the formula for the Sn plus 1, right? Sn plus 1 would be Sn, the sum of the first n terms, plus what? The nth plus 1 term, right? This is adding up the first n terms. This is adding up the first n plus 1 terms. So it's got all the first n terms, and it's got one more, right? And that one more is a n plus 1. Somehow I've got myself reversed from the way I usually do this, but that's okay. Now, for the sum of the first n, I'm going to use the formula. Okay, the part of math induction says assume it works for n. That's assume. When I put in n squared in the place of the sum of the first n terms, I just assumed it worked for n. Okay, that's the assumption part. So right now I'm going to say n squared, and if this is the a sub n, what is the a n plus 1? Okay, how would I turn this formula into the a n plus 1? In place of the n, I'm going to put n plus 1, right? Just like we did in that first example. So this will look like 2 times n plus 1. That's not n plus 1. 2 times n plus 1 minus 1. And that should equal the, now if this is the formula for Sn, what would that formula look like for Sn plus 1? This formula right here. If that's for Sn, what would the Sn plus 1 look like? Yes? Used to stretching? Right, that would be the n plus 1 squared. Okay, now this we don't know to be true. Right, so what we have to do now is show that the left equals the right. So what we will accomplish by showing that the left side equals the right side is we're going to show that by assuming that the formula worked for the first n terms, we're going to be showing that it works for the first n plus 1. Right? And that's the link. We've already shown it works for 1. So once we establish this, that means it must work for 2 and 3 and 4 and for every number after that. So at this point, you have to either do all the work on the left so that it looks like the right, do all the work on the right so that it makes it looks like the left, or make them both meet in the middle. But somehow or other, make the left equal the right. And right now, let me work on the left-hand side. N squared plus 2n plus 2 minus 1. That is n squared plus 2n plus 1. Okay, well, that's factorable. How does that factor? N plus 1 squared. Okay, now we just showed that the left looks like the right, is the same as the right. So by doing that, we showed that by assuming that the formula worked for the first n, it actually works for the first n plus 1. So there's the link between any two particular terms in the sequence. You know, if it works for one, it's got to work for the next. And since it already works for one, it works for everything. On the next one, I'll be a little more, I'll do it the way I usually do it, because I got a little off track there. Okay, let's try to do the same thing for this one. Okay, first to do the easy part, see if it works for n equals 1. Okay, so let's see. For n equals 1, and I'm not even, for n equals 1, the first term is 5. The sum of the first term is 5. So go over here to this formula and see what you get, right? For n equals 1, you're going to get 1 times 1 plus 4, which is 5. Check. So it works for the first for n equals 1. Okay. So this is what I usually do, right? I'm going to come through. I'm going to label this. This is the AN. This is the SN. Okay. I need to show that SN plus AN plus 1 equals SN plus 1. Now, the SN I've already got. That's right there. I need to know what is the AN plus 1. If this is AN, what is AN plus 1? 2n plus 1 plus 3, right? 2n plus 1 plus 3, which is what? 2n plus 2 plus 3, which is 2n plus 5. Okay, I'm also going to need the Sn plus 1, right? If this is Sn, what is Sn plus 1? Okay, Sn plus 1 is n plus 1 times n plus 5. Right, that's n plus 1 plus 4. So now I've got everything I need to plug into this right here, right? I'm going to take that first step and I'm going to replace S sub n with the formula we're trying to prove, right? So I'm going to replace this here, n times n plus 4. And that is the step where I'm assuming the formula works for n. Okay. And now I can add the AN plus 1 is plus 2n plus 5 plus or equals n plus 1 times n plus 5. Is that right? Yeah. N plus 5. Now, at that point, to be truth, I should say question mark. I don't know that that's true. That's what I'm trying to prove is true. If I prove it's true, then I've proved the formula. Okay, so again, I'm going to work on the left. You could do whatever, you could FOIL this if that got you, anywhere. But I'm going to work on this side. That will be n squared plus 4n plus 2n plus 5, which is n squared plus 6n plus 5. Now, let's say you're not any good at factoring, so you FOIL the right-hand side, right? Then you would get n squared plus 5n plus n plus 5. N squared plus 6n plus 5. Okay, so we made the left equal the right. That proves it's true. Check, right? Check. So now we can say that this formula works for all values of n, and n is counting numbers. I guess one way to write it, you could write like this: the sum from I equals 1 to n of our formula 2i plus 3 equals n times n plus 4. True for n greater than or equal to 1. Usually when you do proofs, right, whenever we used to do proofs, then you always had to end by doing this. QED, which I think is like Latin for quo stratum demonstratum or something like that, It's like that which we set out to prove has been demonstrated. Done. QED. Okay, let's do another one. Okay. So first step, check it works for n equals 1. Okay, well, what is the first term? A1 equals, which is 0. 0. So it's the sum of the first term better equals 0. Okay, we'll come over here and use the formula. For n equals 1, it's going to be 1 times 0 times 2 over 3, which is 0. So check. Works for the first one. Okay, this is the formula for an. This is the formula for Sn. What would be the formula for an plus 1? If this is the an, what's the formula for an plus 1? N plus 1 times n plus 1 minus 1, which is n. So it's n plus 1 times n. And if this is the Sn, what is the formula for Sn plus 1? Okay, which would be n plus 1, right? N plus 1 minus 1 is n. N plus 1 is n plus 2 divided by 3. So now again, I would always write over here that Sn plus an plus 1 equals Sn plus 1. I mean, that's true no matter what. If you add up the first n terms of any sequence and you add the next term, it should be the sum of the first n plus 1 terms of the sequence. Okay. Now we plug in. The Sn is this. So this goes here, right? And I'll plug that in, n times n minus 1 times n plus 1 divided by 3 plus an plus 1, which is n plus 1 times n equals Sn plus 1, n plus 1 times n plus 2 over 3. Okay, question mark. Right. Again, I assumed a formula worked for the first n terms, and now I'm going to try to show it works for the first n plus 1. How could I simplify this? Multiply times 3, right? I mean, I think we've been through this even with the systems of equations, that, right? If you got decimals or fractions going on, take a step and get rid of the fractions, right? In this case, multiply both sides, which means every term by 3. So this, on this term here, I'll just go like this, say, times 3. The first term, the 3 cancels in the denominator. N times n minus 1 times n plus 1. Okay, what about the next term? Yeah, you got to multiply that one times 3 too. And it doesn't have a denominator of 3, so it's not going to cancel anything. It'll just be 3 times n plus 1 times n. And on the right, the denominator cancels. Where? Here? Over here? This in here? No, we're multiplying this term times 3. Right? And this is n plus 1 times n plus 2. So again, now we have to just try to make the left look like the right. Okay, so let's see. You know, what I would do right away, notice that every term there has got an n and an n plus 1 in it, right? So what I'm going to do on the left, I'm going to factor from both of these terms, n times n plus 1. Yeah. So I'll write it like it looks like on the right. This is n plus 1 times n I'm factoring from both of these. Okay, well, what's left when I take the n times n plus 1 from this term? The n minus 1, right? If I factor these two over here, then what's left is the n minus 1. Okay, and then what's left if I factor the n and the n plus 1 from here? 3 plus 3. Okay, so now simplify what's inside the parentheses. Now we've got n plus 1 times n plus 2. And that is the same. I mean, my bet is that most of you would not have thought of factoring like that to get that done. It doesn't matter. You don't have to, right? You could have just, foiled all this stuff, multiply these two together, then multiply times n, combine like terms, do the same thing on this side. It will be the same thing. But just noticing that that had the n plus 1 times n, and both of these already had that, I knew all I had to do was make that n plus 2. And when I factored these two out, right, that's exactly what that was left behind. Easier than combining like terms and all this stuff. So we can say, because we showed it was true for n equals 1, we showed that if we assume it's true for n, it must be true for n plus 1. It must be true for all n. And I'll just say QED. Done. I don't care. Just make sure you've checked for n equals 1. There's one more, and then I'm done. No, it's not even one more. That was the last example that I've got. All I was going to show, I mean, we could do one of these just for fun. The fifth one. So we end up using these formulas later on, and we just assume that they're true. I mean, we could tell that something like this is arithmetic, but we use this formula. We just say, yes, this works. So the fact that we've actually taken a step out in this chapter and proved it, maybe that helps a little bit. But in the end, if nothing else, it is somewhat of an application of sequence and series and something different than you've seen before. So that was it. We used math induction to prove statements true involving positive integer n. There's only 3 homework problems, right? This is for anybody who wants to be challenged. You could see what does it look like I'm adding up here? AR to the I minus 1. What formula is that? Yeah, it's the nth term of a geometric sequence is generated times with that. Now, if I set my index I to go from 1 to n, that's adding up the first n terms of a geometric sequence so that we say that it has this formula. So you can use math induction to show that that's true. So if anybody wants to play around with it, you're just doing the math induction like I showed you in the examples here. This is just an extra thing for anybody who would like to see, because it does work for that. What's that? No completing the square.